So our next speaker is David Wilson, who recently moved to the University of Colorado Boulder. He will talk about the discovery of a young pre-intermediate pulsar. You can go ahead and share your screen, David.
Hi, great. Can you hear me okay?
Yeah, and we see your presentation in full screen.
Great, thanks.
Oh, good.
So yeah, hi everyone. As Ingrid said, I want to talk to you today about our discovery of a young pre-intermediate polar. And firstly, I want to thank the organisers for this excellent conference series. It's been really good to have a chance to catch up with what everyone's doing while we can't see each other in person. Yeah, and as Ingrid said, I'm David Wilson. I've recently moved to CU Boulder, and this is work I've done with all of these nice people. And the paper is on archive if you want to read it. To summarize my talk in one sentence, we've discovered the first unambiguous example of a young magnetic white dwarf in a detached post-common envelope binary, making it a pre-intermediate polar. So I'm going to talk about the background behind magnetic white dwarfs and binaries, why this discovery is significant, and look in detail at our discovery and the data behind it. So firstly, I want to talk about magnetic white dwarf incidence. Plenty of white dwarfs are magnetic with fields of hundreds of kilogauss to megagauss, many megagauss. And the rate at which white dwarfs are magnetic varies depending on the kind of system we find them in. So in isolated white dwarfs, we find about 20–25% are magnetic. That's from the recent study by Bagnall and Landstreet. You're looking at the 20 parsec sample, I believe, but that's consistent across many samples, with some evidence that that changes over time. Older white dwarfs maybe have a higher magnetic instance, but yeah, around 20–25% at single white dwarfs. At the cataclysmic variables, which I think is the best named object in astronomy, these are white dwarfs that are accreting from a main sequence companion via Roche Lobe overflow. There we find about 36% are magnetic, again from a volume limited sample by Anna Pala. So slightly higher than single white dwarfs, but of the same rough area. Moving on to the detached post-common envelope binaries, so white dwarfs that have been for a common envelope with a companion but are not accreting through Roche Lobe overflow, we find that the incidence rate is approximately 0. So Liebert et al. Looked at 1,700 white dwarfs from SDSS and found none of them were magnetic. This is a complete mystery, especially as these objects presumably represent the progenitors of the CVs. Why did the CVs have a 36% magnetic incidence and the post-common envelope binaries have none? Conversely, you say, okay, maybe the CVs, maybe their magnetic field is produced by the Roche Lobe overflow accretion in some way. But then why don't you have a 25% value from the single white dwarfs? Note here, I'm not discussing wide binaries. We don't have really good enough data to suggest the incidence rate on them yet, but there have been a few examples found of magnetic white dwarfs in wide binaries. Yeah, so this open question for some time now of why do we see no magnetic white dwarfs in detached close binaries? As a small aside, these magnetic CVs are divided into two classes. So the magnetic field is about over 10 megagauss. This is most of them. They're known as polars, and they have no accretion disks. They accrete material from their companion directly along the white dwarf magnetic field lines onto the poles of the white dwarf. And the white dwarf rotation period is locked to the orbital period. At less than 10 megagauss, we have the intermediate polars. These do have an accretion disk, but it's truncated, so the the accretion disk goes into some radius, and from there on, the material moves along the magnetic field lines onto the white dwarf, as in the polars. These objects are very mysterious because that disk obscures the white dwarf, so the exact characteristics of the white dwarf, such as the precise magnetic field strength and the mass and temperature of the white dwarf, is very hard to measure. What we do know is that, unlike the polars, the intermediate polars have very high rotation rates relative to their orbital periods. The rotation rates can go down as few as minutes. There is some exceptions to the statement that there are no magnetic white dwarfs in binaries. So there's around 17, depending on what you define or what you believe, is done. No magnetic white dwarfs in post-common envelope binaries. I'm showing here the distribution of effective temperature, magnetic field strength. So we can see that they're all, except one, are all in the polar range, and they're all quite cool, ages of quarter of a gigayear or more. These are described as pre-polars, so the assumption that they'll evolve into polars, but all of them are in the right configuration to have been CVs in the past, to have been accreting via Roche Lobe overflow in the past. And so this suggests that maybe that they are not pre-polars, but instead dormant polars. And this is a model by, this assumption was taken up by Schreiber et al. In 2021, and they came up with a formation mechanism for this, where you say, okay, yes, in fact, all of these stars were CVs in the past, and the magnetic field is generated by a combination of spin up from the accretion and the crystallization as the white dwarf ages. This will explain why all these prepolars are old, they have to be crystallized, and why they all could have been CVs in the past. And then they suggest that single magnetic white dwarfs instead are formed by mergers. And this would nicely explain why there are no detached magnetic white dwarfs in binaries. You either have to have undergone accretion in the past, or you have to have a merger, and then that requires a system that a trinary system where you have two stars that merge, and then a third companion that's close enough to form a post-common envelope binary. That configuration isn't necessarily possible, but it would certainly be rare. So that would neatly solve the mystery of why there are no young magnetic white dwarfs in binaries. So now we found one. This is CC Cet. I'm showing here an animation of the system. This is to scale, both in size and orbital separation, size of the two companions, and orbital separation. Have a white dwarf about 25,000 Kelvin, so quite a young white dwarf, cooling age of 0.1 gigayear or so. And its orbital period of just under 7 hours with an M4.5 companion. And I'd like this to show you scale models and see just how small these systems are as would fit inside the sun. And we targeted this with an HC program to measure wind accretion onto the white dwarf from the companion. And this is the HT spectrum we got, and you can see we were successful. We have plenty of metal accretion lines onto this white dwarf, particularly carbon and silicon. But if we look closer at these, we find the lines don't look like any other white dwarf. So we're comparing here in all of these plots. I'm comparing CC Cet with LMCOM, which is another binary observed in the same program with a similar effective temperature and log G. And here you're looking at the silicon line at 1264 angstroms, and it's clearly different from the line in LMCOM. And this is clearly showing Zeeman splitting. So this is where the line is split by the magnetic field into different components, and the amount the line is split by is proportional to the magnetic field strength. And we can fit a model to this using the Zeeman code developed by John Longstreet, and we imply a magnetic field around 600 to 700 kilogauss. This puts it in the intermediate polar range, and thus we see that CC Cet is a pre-intermediate polar. This line is repeated at other, the splitting, sorry, is repeated at other lines. So here I'm showing the silicon 4 lines. You can see there's very deep, well-defined lines in LMCOM are split into multiple components in CC Cet. And then in so the silicon 3 lines, it's just a mess. Each of these close together silicon lines in non-magnetic white dwarfs, each split into multiple components, all overlapping, making this forest of small accretion lines. And again, we can model this, and we find the same kind of results, 600 to 700 kilogauss, result consistent across all lines. And we actually find it in optical data as well. So CC Cet was observed at the SPY survey about 20 years ago, over 20 years ago now. And we look closely at the Baumer lines, and we can see magnetic splitting detected in the hydrogen Baumer lines. With the caveat that there was a large amount of interference. You can see the contribution from the companion there. And the signal mode isn't great, so I don't know if we'd have confidently said this was a magnetic white dwarf just looking at the optical data if we hadn't already known that it was magnetic from the UV data. So it's not surprising that it was missed in the initial survey of this data. But it does raise the question of how many other magnetic white dwarfs are hiding in archival optical data. It's not only magnetic, it's also moving fast and changing. So the lines are very broad. We measure a rotational velocity of about 40 kilometers a second, putting an upper limit on the period of about 2000 seconds. We also, through a series of lucky events, got 2 spectra of this object, and we find the magnetic field is somewhat different. Best fit magnetic field varies from just over 600 to just over 700 kilogauss between the 2 spectra. And we suggest this may be that the magnetic field is offset from the rotational axis, and so each exposure was seeing a different net magnetic field over the surface, over the visible surface of the white dwarf as it rotated. This variation then implies the rotation period can't be much, can't be, really probably has to be longer, or can't be any slightly shorter than the exposure time. Otherwise, if you had multiple rotations within one exposure, then these differences would be smeared out over over the rotation, over the exposure even. So we can actually constrain the rotation period pretty tightly to around 1800 to 2000 seconds with those 2 limits. Interestingly, this means that the rotation period to orbital period ratio is about 0.05. This is consistent with the intermediate polar population. So not only does this star already have the magnetic field of an intermediate polar, it has the fast rotation of an intermediate polar, despite not undergoing accretion. And it has never undergone accretion. So we ran Mason models of binary evolution, and depending on your, so I'm showing here the orbital period as how the orbital period decreases with angular momentum loss as a function of age. And we find that depending on your input for the prescription for the angular momentum loss, CC Cet will not become a CV for over 7 gig a year. So it's nowhere near Roche Lobe overflow. It almost certainly has never been a CV in the past. Which means that that crystallization spin-up model really doesn't work here. It's too young to have crystallized, and it has never accreted. So how do you make it? So as I said, this crystallization spin-up model, that doesn't work. It's too young and it's never accreted. Could it then be a fossil field from the stellar merger? maybe, but so the idea is then it's a merger project. The white dwarf was a merger of two stars and then became a post-common envelope binary afterwards. It seems unlikely there, as the mass of the white dwarf is only 0.4 solar masses. So on the low end for a white dwarf, they're not unusual for PCEB. Magnetic white dwarfs, on the other hand, have a higher mass than average. So it's not impossible that you could have a magnetic white dwarf with low mass, but it seems unlikely that this would be both an unusually low mass white dwarf and in that unique configuration needed to make a merger project and a post-common envelope binary, and for them to be the only one we've ever found, just seems unlikely. And it doesn't explain the spin up. This model doesn't explain the fast rotation. So then we feel that the most likely explanation is something happens within the common envelope, and this a model of a common envelope dynamo was put forward by Briggs et al. And other authors. This overpredicts their specific model predicts the magnetic field strength for CC Cet by about a factor 30, but based on given that we can confidently rule out the other models, I think that this is the way to look for how to make this magnetic field. And to summarize that, any successful model, we have several things we must explain. What's the field strength, must spin up the white dwarf, must reduce the low mass, and the most important thing is this has to only work occasionally. We can't have a model that makes all post-common envelope binaries magnetic. In fact, we have to make a model that makes most of them not magnetic, and occasionally give one an intermediate polar range magnetic field. So if we compare CC Cet with the known magnetic white dwarfs in binaries, so again, I'm showing this plot of temperature and field strength. If we put CC Cet in this plot, it's actually off the plot. So if I expand it slightly, it's a massive outlier. In fact, 6 sigma in both magnetic field strength and effective temperature. So to reinforce the previous point, if we invoke the same formation mechanism for these two classes of objects, that kind of implies that there's this very large population of magnetic white dwarfs, or just dozens of magnetic white dwarfs in the gap between the two objects that we simply haven't found. So I think it's more likely that there are two formation pathways working here, one to make high magnetic field strength old magnetic binaries, and another to make CC Cet-like objects. And briefly do some small number statistics. So we have about a dozen white dwarfs that we've observed now using the same setup as CC Cet, the COS-G 130M spectrum. Plotting here their gravities and temperatures. You can see that CC Cet in the purple is not an outlier in sample, so we can reasonably compare it to the rest of the sample. But I will stress that this was not chosen to be an unbiased sample. This is chosen, these objects are chosen for observability, where they're bright enough to be able to be reasonably observed in one orbit of HST time. But just taking that sample as given, we find a magnetic field incidence of about 7.7 plus 14 minus 2.5%. So not an excellent constraint, but way more than previous results. For example, Lobe et al. Finding less than 0.1%, looking at 1700 optical spectra. Why discrepancies? Probably the explanation is that magnetic fields are simply easier to spot than the ultraviolet. Yes, this one does have detectable bandwidth splitting in the optical spectrum, but as I mentioned, it'd be hard to say that for sure if we didn't already know that about the splitting in the ultraviolet. And simply many, many more accretion lines in the ultraviolet, and less interference from the companion. The companion's emission lines don't really poke through until you're below about 15,000 Kelvin. So to conclude this series, I think we have discovered the first unambiguous example of a pre-intermediate polar. We cannot explain its formation with any existing accretion formation model even, but we think that interactions within the common envelope are most likely. Hopefully this, and if we find more similar systems, may provide insight into intermediate polars. As I mentioned, it's very hard to directly observe intermediate polars, and so their distribution of mass and magnetic field strength, etc., is fairly unconstrained. If we can look at these objects, especially as they already have the right magnetic field and the right rotation periods, we might be able to gain an idea of the kind of mass distribution, magnetic field strength distribution of the intermediate polar population. So future work, firstly, want to characterize this system in detail. In particular, it'd be nice to measure the rotation rate of the white dwarf precisely, and try and map out the surface, the magnetic field distribution, and see if that can put any constraints with, say, the inclinations of the magnetic field to the rotation axis, the inclination of the rotation axis to the orbital axis, and see if that can put any constraints on the formation model. And we'd like to find more. Yes, we looked at 12 objects and found one that suggests that looking at more of these objects with HT might be quite productive. There's certainly many more post-common envelope binaries that are detectable with HST. Many of the known ones don't have periods, but now that the test spacecraft is returning light curves to these objects, it's actually very easy to detect the periods in that. So there's potential to characterize many more of these systems. And with surveys like Sloan 5 and DESI coming online, we may detect, identify many more PCEBs that are amenable to follow up in the ultraviolet. And yeah, so hopefully we can find more of these objects in the future and get a better constraint on their occurrence rates and some insight into intermediate polars. And yeah, that's the end of my talk. If you're interested in more, that has lots of stuff I didn't mention, like X-ray and test observations this star. Please check out the paper and take any questions. Thank you.
Thank you very much, David. Really nice talk. We have a couple hands up already. Axel Schwuppe.
Yeah, hello. Many thanks for your talk. Question, what makes you confident that this object will turn an intermediate polar? And to my best knowledge, we have not yet measured any range of magnetic field strengths for intermediate polars. So this might be even lower than what we are assuming that might become an intermediate polar. And among the nova-likes at larger orbital periods, there are often discussed the existence of magnetic fields to explain some odd features.
Yeah, so yeah, I guess the first question is, yeah, we think this turned into an intermediate polar because that's the I guess the standard model of these objects. They lose angular momentum over time and eventually will start Roche Lobe overflow and turn into CVs. And when this does that, as we predict in about somewhat over 7 gig a year, then its magnetic field strength is such that it'll look like an intermediate polar. The disk will truncate and it will form a disk. The magnetic field strength isn't high enough to accrete directly onto the down the field lines. It will form a disk, and that disk will be truncated at some point. There is some question about how good that model is. These post-common binaries seem to have a lower mass on average than CVs, so how many of them do actually if they are actually reliable progenitor CVs, but there's really no firm evidence that they're not. So I think, yeah, we think this will become an intermediate polar because it should turn into a CV and will look like an intermediate polar at that stage.
Yeah, thank you.
Yeah.
Next question from Nicole.
Hey. And it's funny because yesterday I just stumbled upon a paper about B471 Tauri was the name. Do you know of that one? Because it sounds so extremely similar to what you are describing, the Zeeman-split in the silicon lines and phosphorylating. And was the
V741 Tauri is an interesting case. So there is, this is why I use the word unambiguous example, because that is very ambiguous. So there's in the GHRS spectrum, which is the old spectrograph on Hubble, there is a line that you can fit with a split line. It's very poor signal noise. And then when we got better spectra with STIS, that line wasn't very well resolved, but other lines that line would predict would be split weren't split. So I'm not sure what the original data is actually showing, but it's very hard to say that V741 Tauri has a strong magnetic field, given that none of the lines that we expect to see showing splitting are splitting, other than that one poor signal noise GHRS spectrum. What I would guess is going on here, and it's speculating quite wildly, is that it has some very low magnetic field. There's the kind that possibly lots of white dwarfs have, but we just simply can't detect them. But in V471 Tauri's case, the companion is so active, it's very active K-dwarf, that it's driving signs of the magnetic field on the white. Also, there are other signs of magnetic activity on the white dwarf that it looks like has a accretion spot, for example. And I would say that the companion is driving that, producing those detectable signs that in all other white dwarfs with that low magnetic field we'd never see. That's, I think, is what's happening there. But yeah, also V741 Tauri is close enough that has undergone Roche Lobe overflow, or may have gone Roche Lobe overflow, so it fit into that spin-up accretion model, spin-up crystallization model from Schreiber, if it is magnetic. Yeah, it's a good start, and someone should really reanalyze that data.
Thank you.
Any more questions? Kepler, hand up.
Yeah, I would like to reinforce your statement that the ultraviolet might be the answer to look for. Because when Ingrid and I were looking at the FDSS spectra, we have the M dwarf was perturbing the lines, like you showed. That was very hard to say if the lines were split or not, because there were many components from the M dwarf. So I like your idea, and I think that using the ultraviolet where the M dwarf doesn't contribute is the way to do it.
Yes, absolutely, yeah. Although one of our sample is 13,000 Kelvin, the M dwarf is significantly contributing emission lines there. So you can only go so far down in temperature before that becomes a problem again.
Any other questions? I don't see any, so I think we can finish here. Thanks again, David. Thank you both the speakers. I'm going to stop the recording.